Okay, so I'm going to walk through the test review, and I hope this helps you catch some of the little details that sometimes can sneak up on you on the test. Okay, so number one, this is find the derivative if it exists. It gives me the graph. You can tell that it's not differentiable at this point because we have a sharp turn. So then I know that the derivative, remember the derivative is only defined where we are continuous and differentiable. It's continuous the whole place, but it's not differentiable at x equals 2. Here's the origin. So I'm not differentiable at x equals 2, so it's undefined. The derivative is undefined. The original function is completely defined, but the derivative is not. Number two, find all critical numbers. When it wants critical numbers, you're going to look for anything that's discontinuous or not differentiable. And this thing is a very smooth curve, has nothing exciting happening, so I don't get any critical numbers from that. But if I gave you a function that did, then you would get some critical numbers from that. So for this, I find the derivative and set it equal to 0, a GCF to 4x, set them both equal to 0, and solve it. The other thing you want to make sure is sometimes I'll give you an interval, and you need to make sure that all of your critical numbers are in your interval. This one I did not, so you can include all of your critical numbers that you find from the derivative. Number three, absolute extrema for just a nice little quadratic on the closed interval. Okay, so this is not Rolle's theorem. This is not the mean value theorem. This is just absolute extrema on a closed interval. I know this is a parabola, but I'm chopping it off from -4 to 4. It is continuous. It is completely differentiable. I find the derivative, and I solve it, set it equal to 0, and solve it. So that is one of my critical values, but I also have to use my endpoints because that's the snapshot, that's the size of the graph that I'm interested in, just from -4 to 4. So make sure that you include those endpoints and the critical value you found from your derivative. To get your y values, you're taking all of your x values and plugging it into the original function to get these, to get your y values, and then you're just picking your max and your min. Number 4, locate the absolute extrema. And that graph is very continuous and completely differentiable. We also are on a closed interval 0 to 5. So the first thing I do is I rewrote my function to look a little nicer for me to take the derivative of it. Then I got the derivative. Well, there's nothing to set equal to 0 and solve, so I get no solutions from finding the derivative. So the only numbers I have are from my endpoints. And again, to get my y values, I'll plug those into the original function to get those, and then I pick my max and my min. Number 5, locate the absolute extreme on the given function on the closed interval -60 to 60, which is huge. This function right here has issues, but if you take the bottom and set it equal to 0, you're going to get negative numbers underneath the root, so i's, so you don't get any issues from that. He doesn't have any vertical asymptotes. So I go ahead and take the derivative. So then I low d high minus high d low over low low, and then I clean a little distributing. I went ahead and knocked the bottom out here when I set it equal to 0, because that's going to go away. I subtracted or added my 60 x squared over, divided by 60, and then square rooted both sides, and I got a very nice plus or minus 6. So that's those two right there. Notice I also included the numbers from my endpoints because I'm on a closed interval. Then to get all of these, I plug my x's into my original function to get my y values, and I pick my max and my min. These numbers are really close to -1 and really close to +1. So the 5 and the -5 are bigger. Number 6, find the absolute extrema of the function. So we're sine of pi x, which is very continuous, very differentiable. Closed interval 0 to 1/3. So take the derivative, and this is a chain rule. So cosine of pi x times pi, then I just pop the pi in the front just to make it look nicer. Set it equal to 0. Divide by pi, the pi goes away. So I have cosine of pi x equals 0. Some of us struggle from here to here. This is just where is cosine 0? And I set pi x equal to all those places. Well, cosine is 0 at pi over 2 and 3 pi over 2. But my interval was 0 to 1/3. Now, mind you, that's not 0 to pi over 3. That's 0 to 1/3. So I type in pi over 2 into my calculator and 3 pi over 2 and get decimals and compare that to see if it's in the window of 0 to 0.3, and neither one of them are. So I don't get any solutions from solving my derivative, but I can use the endpoints of my closed interval. So I use my 0 and my 1/3, and I plug them back into my original to get the y values. Number 7, determine whether Rolle's theorem can be applied on the closed interval. If it can be applied, what are the values C in the open interval from -13 to 13? That's important, the -13 to 13. Looking at the original function, I need to be continuous and differentiable. I'm not continuous because I have an asymptote at 0. So no, Rolle's theorem does not apply. Number 8, same thing. I've got this interval. This guy is very differential, very continuous. The other thing you need to check is you need to make sure that f of a equals f of b for Rolle's theorem. That has to be true. So I find f of -3 and I find f of -2, and they are equal. So I'm good. So then I leave the first one, take the derivative of the second one, plus derivative of the first one, leave the second one. I go ahead and lobster those two together, and then I ran my 2 through them. This one, I wrote it twice and lobstered, and then I combined like terms, and then he factored, and I set them equal to 0. I have to be mindful of my interval. -2 is not in my interval because I'm finding all numbers C in the open interval. -2 is not in that open interval. It's right there on the edge, so I can't include him. So the only C value I have is -8/3. Now let's make sure you understand what that's finding. -8/3 is -2 2/3. So what that means is at -2 2/3, wherever this function is, there's a peak or a valley. Because remember, we set the derivative equal to 0. So we're finding where the tangent line has a 0 slope. Number 9, determine whether Rolle's theorem can be applied. Well, cosine of pi x is differentiable and continuous. I have to make sure that f of a equals f of b. So cosine of -pi/2 is 0, and cosine of pi/2 is 0, so both those are good. I find the derivative. I set it equal to 0, divide by -pi to make it easier. I'm looking for where is sine 0. Well, that happens at 0 pi. And then I did -pi because look at your interval. It's between -1/2 and 1/2. So there's no point going 0 pi and 2 pi. If pi is 3 and some change, 2 pi is 6 and some change. So that's way past 1/2. So I just went pi and -pi, and then I solved for x, so I divided all of these by pi, and I got 0, 1, and -1. Well, these two are not in my interval, -1/2 to 1/2. So the only one I get to keep is 0. Number 10, which of the following functions pass through the point 0, 10 and satisfies that f prime of x is 12? So the derivative is 12. Guys, that's your slope. The derivative is the equation of the slope. So f prime of 12 means my slope has to be a 12. And then this point, this 0, 10, I mean, this goes back all the way to math 1. That becomes your y-intercept. Because your x is 0. So I have to pick the linear function that has a slope of 12 and a y-intercept of 10. Number 11, find a function f of x that has that derivative with a graph passing through those points. Well, I'm looking at my options, and I know that it needs to produce that derivative. A is not going to produce that as a derivative. And E is not going to produce that as a derivative. B is not going to produce that as a derivative. So now I'm here. I'm stuck with C and D, and they both have the same 12x minus 6 as their derivative. So then I'm going to take the 0.56 and plug them into the original function. I'm going to plug 5 in for x and see which one gives me a 6 out. So like for C, to test C, I would go 6 times 5 squared minus 6 times 5 minus 111. And I'm looking for it to give me a 6, and he doesn't. So he's out. And then if I test D, he does work. Number 12, determine whether the mean value theorem can be applied to the function x squared on the closed interval 3 to 9. So if the mean value theorem can be applied, find all c's in the open interval such that the derivative equals the slope through those 2 points. So continuous and differentiable, absolutely, it's a parabola. Now the mean value theorem, I don't need f of a to equal f of b. That's roles. The mean value theorem, I find f of a and I find f of b. So I'm going to get 2 points, and I'm going to find the slope through those 2 points, and I want to find the point where the tangent line is parallel to that secant line. So I find f of 3, that's going to give me 9, and f of 9, that's going to give me 81. And that's just using my f of x. Then I find the slope, so y minus y over x minus x, and that gives me a slope of 12. Okay, so then I take the derivative of my original function, and I take that derivative, and I set it equal to my slope, which if you think about it, it's exactly what we just said over here with this picture. I want the derivative of the tangent line, the slope of the tangent line, to equal the slope that went through those 2 points. So that's why I do that. And again, we've talked about several times about looking at the bigger picture. Don't be just math robots. Make sure you understand why you're doing what you're doing. That way, if you completely blank on a test, you can think through it. You know, what is this saying? So it helps you determine what your next step would be. And I solve it, and I get x equals 6. Number 13, a plane takes off at 2 o'clock on a 2,200-mile flight. After 12.5 hours, the plane arrives at its destination. Explain why there are at least 2 times during the flight when the speed of the plane is 100 miles an hour. Well, find your average speed over the flight. So when time is 0, my mileage is 0. When time is 12.5, my mileage is 2,200. So I find the slope. I get an average velocity of 176 miles per hour. Well, if I want an average of 176 miles per hour, it says explain why there are at least 2 times during the flight when the speed of the plane is 100 miles an hour. Well, I had to hit 100 on the way up to 176, and then I had to hit 100 on the way down when we were getting ready to land, which is what E says. Number 14, a company introduces a new product for which numbers of units sold S is that, where T is the time in months since the product was introduced. During what month does the derivative equal the average value? Okay, anytime you see average value, you know that you're going to be finding the slope. This is during the first year, but time is in months, so my interval is 0 to 12. So I'm going to find S of 0, which I got 500, and S of 12, which I got 1,300. So I now have 2 points, which I can find the slope. So I do y minus y over x minus x, and I get 200 over 3. So that's my slope. It says, during what month does the derivative equal my 200 over 3? So I have to find the derivative of S of t. Well, the 1,500 goes away, and then I low d high minus high d low. And I get this. I set it equal to 200 over 3, and then I cross multiplied. Then I divided by 200. Then I square rooted both sides, and then I subtracted 3, and then I just went decimals. And I didn't put a plus or minus because this is time, and time can't be negative. So 3.7, that'd be January, February, March. So we're into April. 3.7 months. So we're into April. Number 15, find the critical number critical numbers, set the derivative equal to 0 and solve it. I don't have an interval, so I'm not going to get a critical number from endpoints of an interval. Just take the derivative, set it equal to 0, and solve it. Easy. Number 16, identify the open intervals where the function is increasing or decreasing. When you hear increasing or decreasing, you need to automatically know that you've got to go first derivative. So I find the first derivative, set it equal to 0, and solve it. That gives me my two intervals. I pick two test points. I find the derivative where the derivative is in those endpoints, positive or negative, so I know I'm increasing from 1/2 to infinity and decreasing from negative infinity to 1/2. Identify the open intervals where this function, and this one's a little uglier, is increasing or decreasing. Okay, so I rewrite my original interval so it looks a little nicer, but I do need to think about if this guy's going to give me any critical values from the original function. And he does have a square root. That square root can't be negative. So I have to come over here and do this. So the square root has to be greater than or equal to 0. I solve it, and I'm going to get a plus or minus root 30. And if you think about it, I need this to be in between a negative 30 and a 30. If I go beyond 30, that means this number is going to get big. And when I subtract it, or root 30, when I subtract it from 30, I'm going to get a negative number. Same thing if I go outside here. If I go more negative than a negative root 30, and then I square it, it's going to be bigger than this 30, which is going to make the root negative. So I need to live in between here. So I have got an interval of negative root 30 to 30. I find the derivative of my cleaned up function. So leave it alone, take the derivative, this is a chain rule, plus the derivative of the x, which is just a 1, and then the back end. And then let's see, I take all my little guys and multiply them. That's what gives me this. I'm GCFing the negative 1/2, so pull him out. It's going to make him go away, and that's going to take this guy down to 1. So there he is. And then I combine my like terms, pull this guy down to the bottom. And then that becomes the pedestal. That becomes the derivative. When I set him equal to 0, the bottom goes away. Subtract your 30, divide by negative 2, root both sides. So those become my critical values. But also remember that you created an interval based on the original function. So I can't go beyond negative root 30 and positive root 30. And I also have these critical points. So that's what creates these three intervals. I get decimal values for all of these, so I know how to pick my test numbers. And then I go back into the original derivative and just figure out signs for whether I'm increasing or decreasing. Be careful on number 17. Make sure that you would have caught that you've got to deal with creating an interval for this thing to stay positive. Number 18, for the function, find the critical numbers. So the original function has no critical numbers. It's very boring, nothing exciting going on. We are continuous and differentiable. So I just take the derivative, set it equal to 0, and solve it. So those are my only critical numbers. So we've done that. Find the open intervals where we're increasing and decreasing. So again, I find my intervals, get my test numbers, and I plug into here, and that's where you can see the negative, negative. So negative, negative would give me a positive. So I'm just doing my test numbers. And then I can tell, since this is increasing and then decreasing, that at 0, it's going to be a relative max. And then this one is decreasing and going to increasing. So I know at 8, it's going to be a relative min. And then to get these numbers, you're taking your 0 and your 8 and you're plugging it into the original function. Number 19, find the relative extrema for f of x. That's just a very nice opens down parabola by applying the first derivative test. So I find the first derivative, I set it equal to 0, I solve it, I get a 3. It creates my two intervals. I pick numbers in those intervals, throw them into f prime, and find if I'm positive or negative. So at 3, since this increases and then decreases, I know I'm going to be a max. And then to get my 83, plug back into the original function. Okay, number 20 is a great problem, and it really makes sure that you're stepping back and seeing the big picture. It says the graph of f is shown in the figure. Sketch the graph of the derivative. And I know these graphs are fuzzy and it's really hard, but it says graph of f of x is shown below. So this is f of x. Now, if we're looking at the first derivative tells me increasing and decreasing. Okay, so look at your original function. He is increasing always. So I know that f prime is positive when f of x is increasing, and I know that f prime is negative when f of x is decreasing. Well, if we're increasing always, then f prime needs to be always positive. Well, this guy is below the x-axis. He's negative the whole time. This guy's above the x-axis. He's positive the whole time. This guy goes from negative, from below the x-axis, to above it. So he goes from negative to positive. This guy stays positive, but right there he hits 0. So that would have to be like an inflection point. This guy's decreasing, or going from positive to negative. So that would have to go from increasing to decreasing. So B is the only one that stays positive the whole time. And again, D does not work because it comes down here and hits 0. 21, kind of the same thing. It's just got a little bit more action going on. The graph of f is shown in the figure. Sketch the graph of the derivative. So this is f of x. Okay, so I am decreasing to there, which would be there, or maybe a little bit here. I know it's fuzzy. So I'm decreasing from negative infinity to negative 1.5, and then he's increasing. So he's increasing from negative 1.5 to 0. Then I'm decreasing from 0 to 1.5, and then I'm increasing from 1.5 to 0. So for all of my decreasings, I need my derivative to be negative. For all of my increasing, I need my derivative to be positive. Okay, so let's check C. Negative to 1.5. Positive from 1.5 to 0. Negative from 0 to 1.5. And then positive from 1.5 to infinity. So really make sure that you understand that relationship. Find the points of inflection. As soon as you see the words inflection, you're thinking concavity. So you're thinking second derivative. So if I'm looking at the second derivative, the first thing I need to do is find the second derivative. And we're only on the interval from 0 to 2 pi. So if you look at my work for number 22, we're continuous, we're differentiable. I don't need to worry about any of that. I find the first derivative. So the negative sign will go negative cosine, and cosine will go to a negative sign. And then I go right on to my second derivative. So negative cosine would become a sine, and negative sine would become a negative cosine. Then I'm going to set this equal to 0. And there's no double angle formula here. There's no Pythagorean here. I just have to solve it. So I'm going to set them both equal to each other. So I added the cosine x over. So where does sine equal cosine in this interval? Well, it happens here and here. Here where they're both positive and here where they're both negative. So that would be pi over 4. And then this would be pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So that's where you get those two from. So then I make my chart with my critical values in there. I'm picking values. So between 0 and pi over 4, that's the little guy, pi over 6. Between pi over 4 and 5 pi over 4, I'm picking pi because that's the nicest one there. And then from 5 pi over 4 to 2 pi, I'm picking 3 pi over 2. And then I take these and plug them into the derivative, which is this guy. And that's what I'm doing here. This is my chicken scratch. So sine of pi over 6 minus cosine of pi over 6. And you can see my values here. And I just need to know if they're positive or negative. So just really make sure you're good. You don't want to do all this right and then miss it on your trig. So just be super careful. So then I get my signs in here, and I can make my conclusion. Number 23. Find the points of inflection and discuss concavity for that guy. Okay, well, that guy has issues. He is, I rewrote him like this. I need the x plus 16 to be greater than 0, so I just need x to be greater than or equal to a negative 16. So this becomes where he lives, so negative 16 now becomes a critical value. And then, so then I take the derivative, and again, that's pretty straightforward by this point. Just some algebra, a little GCF of the negative 1/2, little common denominator, no big deal, because then you've got to go into your second derivative. So there's the low d high minus high, and then here's the d of the low. Technically, there's a 1 out here because it's a chain rule, over low, low. Clean up the little guys. These cancel, so again, I'm leaving this in parentheses. And then I squared him and squared him, which gave me that. I'm not going to distribute that on the bottom because I know I'm going to take a 1 plus 16 from everybody. A GCF and x plus 16 to the negative 1/2 out. That's going to leave me with a 6. And then 1/2 minus a negative 1/2 is going to give me a 1. And then it's going to leave me with this guy. It's going to take this guy completely out. But watch this right here. That's a shark. You've got to distribute that through. I'm going to move this to the bottom, and that's why that's a 3/2. I distribute here and distribute the negative there, and then combine my like terms, and this is my second derivative. When I set that equal to 0, the bottom goes away, and I subtract 64 and divide by 3, and I get negative 21.3. Well, negative 21.3 is out of my domain. So all that work, and I don't get to include him. But I'm going to be looking for all that work. You've got to have the first derivative right, the second derivative right. You've got to have him right. You've got to tell me that he's out of your domain. I don't even care if it's multiple choice. You've got to show me all this work, because this on the AP test could be a free response. So the only critical value I have for this function is the endpoint of my domain. And so I plug in a 0 because that's the nicest, roundest number in there. And it's positive so that I know that we are concave up for the whole life of this graph, which means he has no inflection points. Now, you have a graphing calculator. You could graph him, and you'll see that he does something like that. And this is your negative 16. And you'll see that he's, oh, wait, concave up. So he does something like that and stops at negative 16. So you'll see that he's concave up for the whole life of his graph, which means he has no inflection points, because an inflection point is where the concavity changes. Okay, 24, find all points of inflection on the graph. All right, inflection, points of inflection means concavity, which means I'm going second derivative. So I go for, well, he's continuous and differentiable because he's a nice easy x to the 4th. First derivative, I go right into my second derivative. I don't have to worry about domain. Everything's defined everywhere. Set that equal to 0 and solve it. Get my 2 critical values, throw it into my chart, pick my test values. When I'm finding these, I'm not going here. I'm going here because I think it's easier to find my signs and draw my conclusions. I know that I'm going to have an inflection point at negative 2 and one at 0. This is increasing and then decreasing. So I know that's a max, and I know that one's going to be a min. And then to get the y values, I just plug it back into the original function. 25, find all relative extreme. Use a second derivative test where applicable. Okay, now this one is tricky, I think, because it's alluding to the fact that you need to use the second derivative test. Okay, but again, focus on the big picture. Read the first sentence. Find all relative extrema. That's not inflection point. That's not concavity. You don't need the second derivative test. You need the first derivative test to find your extrema. It's wanting you to use concavity to determine if it's a max or a min. Well, we can do that right off the first derivative test. So again, make sure you see the big picture. So I'm going first derivative test to find his extrema. So first derivative test, set them equal to 0, factor it, solve it. Throw it into the chart, pick your numbers, find your signs. These are both negative, so no max or min in there. From here, I'm going from decreasing to increasing, so I know that one's going to be a min. It's going to happen at 12, and to find that big old number, you plug it back into the original function. 26, the graph of the function is shown below. Sketch the graph of the derivative. Okay, so if this is the original function, then it's decreasing, let's see, from negative infinity to negative 1.5, and then increasing to 0, and then decreasing, and then increasing. Okay, well, f prime needs to be positive when f is increasing, and f prime needs to be negative when it's decreasing. The whole positive and negative is just above and below sea level. So if I'm decreasing from negative infinity to negative 1/2, I need to be below. I need to be negative. Then it becomes increasing. Okay, well, then the derivative needs to be positive. So just make sure, again, this is just another one of those where you need to make sure that you see that relationship. 27, I've got increasing, and then I've got decreasing. So I'm increasing from negative infinity to 0. I don't know if it actually gets to 0. Decreasing from 0 to positive infinity. So f prime needs to be positive where I'm increasing and negative where I'm decreasing. So positive just means above sea level. So positive here and negative here. And that's the only one that does that. 28. The graph is shown below. F is decreasing always. The whole function is decreasing. So f prime needs to live below sea level. It needs to be negative. And D is kind of hard to tell. This is your axis, your x-axis, and this is the graph. So it is below sea level. So it needs to be negative always, and it's the only one that's negative the whole time. Okay, graph is shown below for which values of x is f prime equal to 0. Okay, again, this is a big picture question. If f prime equals to 0, then that means that the slope of the tangent line is 0, which means we need to have a horizontal asymptote. Well, that would happen here and here. So that happens at 0 and 4. The graph of f is shown below for which value is f double prime. So the second derivative equal to 0. Okay, well, what do you do when you set the second derivative equal to 0? Well, you're doing the second derivative test. Well, where it actually equals 0 is where the concavity changes. Those are your inflection points. So where does the concave down change to concave up? And that happens right there at -2. And then the last 4 are describe and detail and graph. These are your curve sketching problems. I'm not really going to talk through these because they're in so much detail in my work. Like on 31, make sure you know how to find a slant asymptote. Make sure you know all the parts. You don't have to label them A, B, C, D, E. And you don't have to do this part. This is just me showing you how all the information that you're finding is coming together. When you find intercepts, I want to see them on your graph. These are the details that I'm going to be looking for. Make sure it's all there. Make sure it's super clear, easy for me to read, to find all the information. So take your time and walk through these super carefully after you've done them yourself. And then obviously, as always, if you have any questions, you're welcome to come see me and I'm happy to help.